Start dynamic programming here. And this is where we started talking about the change making problem, okay? So again, imagine we don't have the US coin system, but we're in some weird country. We're off in Barlandia, and they have pennies and 3-cent pieces and 4-cent pieces, and that's all. And now you come along and you need to give somebody change. You owe them 11 cents. How many coins do you need to give them 11 cents back? Hey, two 4 cents and a threepence. Two quarter pences and a threepence coin will do it. So 3 coins will do it. You need to give somebody change of 6 cents. How can you do it? And again, you might say, hey, well, I need to give you 6 cents back. I'll give you a 4-cent coin. That's doing pretty good. That seems like I'll give you the most I can with a single coin. But then I'm down to giving you 2 1-cent coins. I would take 3 coins. If we're a little bit clever, we can say, hey, 2 3-cent coins can get me the answer more easily. Okay, so with the US coin system, I noted the greedy algorithm works, giving as many quarters as you can, and then after you give them all the quarters, you can give them all the nickels you can. Then give them all the dimes you can, then all the nickels you can, then all the pennies you can. That is the most efficient algorithm. It turns out, based on the 1, 5, 10, 25 values of coins, if you have different values of coins, it's not necessarily the easiest, the most efficient to do that greedy algorithm. In general, it's a much tougher problem, okay? So I think last time we saw this code here and we started looking at it, and that's where we left off. If you look at my little webcam, we ended up with, we had some picture that looked like the computation tree for, hey, I want to give 6 cents of change. And what did our algorithm do? Our algorithm is just going to search all possible ways of making change. We're going to loop through for every coin value. There's 3 of them in this case, but for each of those values, if, and this should actually be a less than or equal, if the coin is less than or equal to the amount that I know, then go ahead and try it. Try going ahead and giving that 1 coin, hand over 1 coin, and then say, gosh, well, I still have, so maybe I hand over a threepence. Okay, well, then I still have, I owed you n cents before, now I'd owe you n minus 3 cents. And we try that. We also come by, now this is gonna be inside a for loop here, and I'm gonna try doing it for a single penny, C being a single penny, and for C being a 4-cent piece. I'm gonna try all 3 of those and keep track of the fewest coins needed out of every single thing I try. So, do you remember that water pouring problem? I'm realizing as I prepare these lectures, I'm really glad I included that homework assignment, because that I think is foundational in that we did a breadth first search and reviewed that state space as a graph, okay, of the jug pouring and every configuration. And we did say a breadth first search. You could also do a depth first search. And say, hey, yeah, I'm at this location. Let me look at all the places I can go in a single step. That's what we're doing here too, in some sense, okay? We are looking at the state space here is sort of how many coins I have remaining, okay? We store with that, the answer associated with that. So, hey, but if I have 12 coins remaining, I have a certain answer. If I have 3 coins remaining, and I'm doing this, I'm going to every node. I'm starting at this node N, okay? And I'm searching through all its children. What are its children? If you have to give N cents of change, your 3 children nodes are N minus 1, N minus 3, and N minus 4. And so this is a search. What type of search is it? Is it breadth first search or depth first search? I claim calling N, like calling coins, is kind of like calling a search algorithm. The graph you're searching, every node is an amount of money you want to make change for. So what do you call it?
Would it be a breadth first?
So breadth first says, hey, at a certain node, compute all the things that I want to visit next, three other, so I'm at node 17 cents. I need to give change. My children are 16, 14, and 13. And so breadth first would put those into a queue and say, okay, visit 16 and then go visit 14 and then visit 13 before you visit any of the children of 16. Okay, so I think that's not quite what we do, because what do we do here? We go ahead and call, we don't actually keep any explicit stack or queue, but what is going on? A recursive call. There's a runtime stack going on. This is exactly the code for depth first search. For every child, go and call depth first search on every child. Okay, and so I'm sitting here at I have 17 cents of change to give. I go ahead and recur on, I'm going to make that 3 recursive calls overall during this loop. I'm going to look at the 3 children of 16, 17 minus 1, 17 minus 3, 16, 14, and 13. I'm going to look at those 3 and then take the minimum out of those 2. But when I go ahead and recur on 16, 16 is going to go ahead and start looking at its 3 children, including 15. And I'm going to look at these 3 children here, but before I come back and look at the next child of 17. And so when we had this tree here, so now we'll switch over to my webcam and double click and make that larger. I guess I should unmute and then mute myself on the other one and make it clearer. If you guys are good with double clicking, let me know. Send me an email. By switching microphones and stabbing at buttons, I could make my cell phone cam come fully online. But
double clicking works fine.
Okay, cost of 6. Barlin, shut up. You talk about this too much every time. Coins of 6 had 3 children, coins of 5, 3, and 2, and we went ahead and we recur on coins of 5. To do coins of 5, that recurred on coins of 4, coins of 2, coins of 1. So this is our picture we had before. We started drawing all over it. Coins of 4 started recurring, coins of 2 recurred to coins of 1. Coins of 1 recurred to coins of 0, and so on. And then we came back with the whole answer from going to coins of 5, and we made another call down to coins of 3. Now, wait a minute, coins of 3 had actually already appeared over in this tree here. Okay. But we go and recur on this. So really, coins of 3 and coins of 3, these were 2, if you think of this as a graph, this was the same node, and I visited it coming once from here and once coming from here. Okay. Once from C of 6 and once from C of 4, state 6 and state 4. Okay, so we talked about this graph last time, and so we're saying, look, there are huge amounts of repeated computation. C of 2, we eventually visit C of 2, even though C of 2 was visited over here, and C of 2 was visited from the one that was inside the C of 3 that was over here, and it was called directly C of 2 here. So C of 2 occurs 1, 2, 3, 4 times in this graph, and I'm researching the graph from C of 2, from node 2, I'm researching that 3 different times. Depth first search, what did we do in depth first search when we thought about properly as a graph? We kept an array of what nodes were already visited, and we didn't revisit a node, and we did that to avoid cycles. Okay, here it turns out this graph is a DAG. For every time you make a move, you really get smaller and you can never get a cycle. But there can be multiple, starting with 6, there could be multiple ways to give change, and you end up in a place where you only have 2 coins. There are several ways you can do that. So really this was a DAG. Some of these C of 2, I got to that node several different ways through several different runtime paths. So here's the observation. 2 ways of phrasing it. One is we have all these repeated subtrees. Okay, an equivalent observation, hey, this is depth first search and we're revisiting the same node repeatedly. Let's use the same trick. So this provides now a solution. Let's use the same trick. Let's keep a list of all the nodes we've already visited. Let's mark a node as visited and never visit it again. Okay, so that's what we're going to do. I'm going to switch to my notes over here. In fact, let me and I even put this in the notes. This on the web page here. So relating it to breadth first search and depth first search. Okay, but so let's use that same notion, the same trick we used in depth first search, and mark nodes we've already visited. In depth first search, it was required to avoid cycles, even if, so if you didn't have cycles, you don't need to mark it. But if you have a lot of shared places you visit, then it still helps to mark it. So let's go ahead and use this. And this is going to be called memoizing. Why memoizing? You're writing a little memo to yourself. Hey, if I get called and I'm asked to solve coins of 3, here's what the answer is going to be. If you ever come back and want to know coins of 3 again, don't go and recompute it. Just look here. I've written down the answer for you. I figured it out once and wrote it down. Okay. So that's what memoizing is. Write down the answer and remember it. So if you're ever asked to solve that same input again. Okay. So here's what we're going to think about. Okay. I have my function coins already written. Okay. That's the, hey, sit down and actually go and solve it. That's the code we had before that did that depth first search. Now here's what I can imagine doing. This is Python code. I'm going to set up, hey, here's a list of all the things I've already solved, which is initially is empty. Okay. This is a dictionary, a Python dict that maps keys to values. The key is going to be what node I have, and the value is what is the answer for that. So if I know that C of 3 ends up being 2, I can, or 1, I guess. If I know that C of 3 is 1, I can associate the value, the key 3 with the answer 1. Associate my inputs and outputs. Okay, so initially I don't have anything associated, but here's what I'm going to do. I'm going to call coins memo. And the very first thing I'm going to do, rather than call coins, I'm going to say, hey, do I already know the answer? Check if n is one of the things in my dictionary, in my hash table. Okay. I'm given coins of 17. Hey, is 17 a problem I've already solved? If so, I'm just going to go ahead and return it. If not, I'm going to solve it and write it down in my notebook. Okay, so does that make sense? I phrase it as an if else, but maybe it's not really an if else, because I know that if either it's already in my book, okay, in which case I can go and return it. If it's not in my book, write it down in my book. And so I don't need this part to be inside an else. I always do this. This is my one return statement. Return, hey, look it up. By the time I reach this blue line, I know it's in my book. I know it's in the hash table of answer called answers. So again, this is a hash table where this is the key and this is the associated value. Okay, so that's the idea behind memoizing. Very straightforward. This is not quite good enough though. Why is this not good? Because say we start with 17. Say, hey, what is coins of 17? Go and memoize. I say 17's not already computed. I've just barely started out. I don't know anything already. Call coins of 17. Well, if that goes up here to this code, then we're stuck in this code that searches the whole tree and does lots of repeated processing. Okay, so let's not do that. Here's what I need to do. I need to go ahead and combine. The problem is that this one recurred on coins, not on coins memo. All I need to do is rewrite this to, when it recurs, go ahead and recur on coins, the memoized version of coins. When you make that recursive call, don't recur back to the unmemoized version. Call the version that checks for previous results. Okay, so that's what we're going to do. I'm going to go ahead and fold those together and get this here. I'll have a global variable where I set up my previously computed answers, and here's my function coins memo that does, now all I've done is, if n is not in answers, here's that exact same previous code we had. Nothing changed here except that I need to change that to be coins memo. And I did that in another file here. Let me go show it to you. I actually wrote it down, and rather than just a text file, I actually wrote in Python and ran it. And that's where I found that I had that. Found 2 different bugs when I actually did it. Need to say less than or equal here. Oops, this is, sorry, wrong one. Here's coins memo. I need to make that a less than equal. I'd done that one wrong. And yeah, I need to update this call to be called the memoized version. Okay. So this goes ahead and gives me this. Let me go and put in some comments here. We're now going to look at different versions. So again, this is, I have a global variable for value of my coins. Here's the first version that was regular old coins. And first of all, I want to have my test cases. And so I wrote my test cases here. That's great. Including the fact that coins of 6 gives that you can do it in 2 coins. You don't need 3 to get coins of 6. Okay, so I did my test cases, and then I came along and rewrote this, and I'm like, great, now I need to do my test cases again, but just called coins memo. So yeah, so here's a little side thing. Do I copy and paste this and replace every coins with coins memo? I could. But I actually know ahead that I'm gonna have a 3rd version of this as well, and then a 4th version of this. I'm gonna have 4 versions of coins that all I want to run the same tests. And if I add any tests, I want to do more. So I actually abstracted all this part out into a function called run tests. And what does run tests do? First of all, I'm gonna have all my test cases, which is, hey, coins of 4 should give 1. Coins of 6 should give 2. Coins of 11 should give 3. Coins of 0 should give 0. Coins of 1 should give 1, and so on. So I have all these test cases here. And then I say, hey, run tests, give me what function you want to test. I'm going to loop through this table and just assert that for every pair in this table, for every amount, comma C in this set here. This should actually probably be a list. There we are. Set or list works either way, but yeah, okay, so this is just a little Python. What makes this possible? It makes it easy in Python and not so easy in Java. It can be done in Java if you know what to do nowadays. The reason is I passed in this function f. And down here, I'm going to call to do run tests of coin. I can get rid of all these now. And then down here, I can just say run tests of coins memo. Okay. So I can now run that, and both my test cases pass. Sorry, run this. And yeah, it looks like an old thing there. Let me just double check here. Okay. This particular editor I see the old errors, and I just want to make sure that, no, I'm getting a new error here. Local variable answers is referenced before assignment. And does it tell me what line? Yeah, give it trace back. Right here, I need my variable answers. Wait, answers is right here. So I run tests down there. So some on line 60, it's sort of saying, did I misspell a variable answers? Okay, well, I'll fix that in a moment. Okay. Sorry, this is really annoying here. This is the only thing I changed right before class. No. This is now weird scoping. I'm going to go ahead and just comment this out. And run it. for all this. Now run it. Now everything is okay. Okay, Python has weird scoping, and this is one of the places where what variable answers was referring to. This was not the global variable. And so, yeah, this didn't work because it wasn't picking up the global variable here, even though it kind of looks like it should. Why? Because I declared it down here. Is that declaring or is that reassigning a global? I need to do something different. I forget what it is in Python. Okay. Anyway, so we run this. It passed all my tests. I didn't get any errors about passing the tests. In addition, by the way, it printed out some timing. Okay. Let's go ahead and, so I wanted to print out, I had a for loop that just printed out how long it takes to call coins of 1, coins of 2, coins of 3, coins of 4, and so on. So I just had a for loop. What do? I go ahead and record this. I look up the system time, save it at start. Go ahead and call coins of I, call the stop time, and then print out all this here. Don't worry about the Python formatting, except that I'll mention that, hey, have people seen the Python format strings before? Here's an example. If you have in Python, if you take a string and you precede it with the letter F, then anywhere in that string that you use curly brackets, it will treat that as code and evaluate it. And that's pretty dang cool. So in here, I just have the variable F and the variable N I want to print out. So I just go ahead and print those out. And that's why we get timing something on 0, something, this format string. Here's another format string here. I just print out each line. I print out I equal sign, and then I want to actually print out the value of I. So I just have I in curly brackets. Then a colon, and then result in curly brackets. And then in a parenthesis, and then stop minus start in curly brackets. And then you can go ahead and do some formatting on it, how many characters you want on that. That's a separate thing. But anyway, Python's format strings are awfully dang cool. The only thing you can't put in curly brackets is another string constant that wants to use. And so you can't have a code that uses strings inside your constructing a string constant. That's actually kind of annoying after a while. It's like, oh, so well. I wish it had a language that let me do both. For my 380 class, you won't be surprised that I'll say, hey, Racket has a way of doing that doesn't have restrictions on what can go inside that computed part. Okay, so print timings. Let me go ahead and print timings, and what printed out, the call coins of 0, coins of 1, coins of 2. We're going to get timing down to the millisecond. So you can see that these all take coins of 1, coins of 2, coins of 3. That's actually a lot of my base cases. But, you know, coins of 8, coins of 11, coins of 12. We searched through this whole tree that we drew out with a lot of, this is the first version that repeated things. And yeah, it runs super fast. You can see it starts to get a little bit faster. When I got up to coins of 19, it took, oh my goodness, nearly 1/100 of a second, but not quite 1/100 of a second. So it looks okay. Let's run that one more time. All I did was up and printed for higher values of I. If you look at this, things are slowing down. Coins of 30 takes 1.6 seconds to complete. Coins of 31 took 3.2 seconds to complete. Coins of 32, we're up to 4.8 seconds. Oh, coins of 33. Looks like it's almost doubling, not quite doubling, but almost doubling every time. Yeah, 8 seconds for coins of 33. Coins of 34. Oh my goodness. This is that repeated. This is the code where we're not memoizing. We're not doing anything smart. And we end up, coins of 34 takes 12 seconds. Coins of 35 is going to take about twice as long. Coins of 50, yeah, I could have started that at the beginning of lecture and still would not have completed it. Okay, so that's that repeated subproblems. We're repeating these subtrees. Coins of 35 is going to call coins of 33 and coins of 32 and coins of 31. And it's going to be the sum of all of those 3 other times going on in there. That's really what happens if each of these times is probably going to be the 1 less, the 3 less, and the 4 less times all added together. I'll at least sort of see if that seems to hold true, but add those 3, and that's about your running time for this. That's pretty bad. Let's look at the memoized version. And since I wrote print timings as a function that takes an NEF, I can just call print timings of coins memo, and I'm going to go all the way up to 50. Let's go to 60. Okay. I'm going to go back to save the time. Take this, comment that one out. So now we're going to print the timings of coins memo and see if it really is faster to avoid computing the subproblems. Boom. Yeah, it doesn't even get up to the single millisecond range. Okay, memoizing is pretty awesome. Okay, so we take this, we were computing so many repeated subproblems that it was just killing us. And now by putting in that simple modification that is like marking the nodes in depth first search, and we get this much better version. Okay, by the way, if you look at this, how does this array answers get filled up? Initially it's empty, right? And then I come along and say I call coins memo of 50. Okay, it's going to go and look at, it's going to call coins memo of 50, is going to call coins memo of, say we go try the 4-cent coin first. It's going to call coins memo of 46. Okay, that's going to recur. Coins, our memoized answers is still empty, so it's going to, coins memo of 46 is going to do this, go through, it's going to call coins memo of 42, which is going to go back, which is going to go back, which is going to go back, which is going to go back. Eventually we're going to get down to coins memo of 2 or something like that. And we're going to say, hey, 4-cent coin is no good, 3-cent coin is no good, try a 1-cent coin. So we'll try coins of 1, go back, still haven't put a single thing into answers yet. We're doing a depth first search and we've gone deep, 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 deep. We've never backed up, but we're about to back up. We got from, coins of 42 all the way down to coins of 2, then coins of 1. Why? Because I can't subtract 4 or 3, so I don't try those. Coins of 1 goes up and says, what is coins of 1? It's not in my table, so do a compute coins of 1, try coins of 0. Coins of 0? Yeah, write down the answer. There's my answer, okay? And then return it. Okay, so now I've finally memoized coins of 0. Backing up here, then it can come back out and it can try some of the other things. Backing out will come up and say, hey, now I know coins of 1 is 1 plus that answer, and it's going to memoize coins of 1. So I've now coins of 1 and 0 memoized. And then it's going to back up to the one that was then went up like 2 and 6 and 10. It was going by 4s. Yeah, it's going to fill in answers of 0, 1, 2, 6, 10, 14, and so on. It's going to fill in all those things into the answers. So when I find as I come out of my depth first search, that's when I record the memoization. I'm going to come, get back a ways, and then I'm going to go and look at the other things I do. But suppose I get all the way back and I've just memoized the multiples of 4. Okay, great. Answers is that table's not totally filled, but I can start filling it in other directions, and I'll hit this loop, my depth first search at the top level, say, okay, we'll try 42 minus 4 didn't work, try 42 minus 3, 39, and that will start recurring. And as I'm doing that, I'm going to hit some of the same subproblems that will come right back from answers. I'm going to find it in answers and jump straight down to here and skip over that whole loop. So what's my point? As I'm filling in this table, if you think about how it gets filled in, it's a little bit filled in a somewhat unpredictable order. I get all these recursive calls pending as the depth first search goes down. And then I might, in this case, answers of 0 is the first thing that actually gets memoized, and then answers of 1, and then answers of 2, and then it goes up to answers. We're computing answers of 6, and then it's going to go look at answers of 5 and start doing stuff there, blah, blah, blah. And so answers of 5 might get filled in before answers of 4 ever gets filled in. The order in which this array answers gets filled up, or this hash table answers, eventually every key is going to be filled up from 0 all the way up to 42. But if it needed them, but the order in which it gets filled in depends on how the running time, how these calls are placed, and how it makes the recursive calls. Okay, so that's great. Here's just another way. I'm going to have one little twist on this of saying, hey, let's be a little bit more methodical and not necessarily use recursion. Okay, here's what I'm going to do. I'm going to give the bottom up, saying, hey, you know, I'm going to go fill this table up in order. I'm going to say, hey, what is answers of 0? Then what is answers of 1, answers of 2, answers of 3, answers of 4? Because then I would come along and, hey, what is answers of 7? If I know that answers of 0 through 6 have all been filled up, then I don't need to actually do any recursion, right? Answers of 7 is just going to refer to the other things in the array that I know have been filled in. So if I fill in this array bottom up, I don't need to actually phrase this as a recursive algorithm. Still based on the recursive algorithm, but so here's the bottom up, BU for bottom up version. So coins memo boo. I'll go ahead and set my answers to be empty, initialize the base case. So this looks a little bit different than before. But then I go through and do this thing here. But here's, instead of making a recursive call, all I do is look up in my table because I know that it's going to be filled in. So memoizing was kind of neat because it was this very rote thing that says, hey, do we know the answer or not? I don't know. Just if not, we go compute it. And if we do have it, then we look it up. And the nice thing about doing that memoizing, it was rote. You can give me any recursive algorithm, or any algorithm, doesn't need to be recursive. Give me any algorithm, and I'm just going to go and modify it the way we talked about this coins memo. You give me this code here, I can turn it into the whole function on this page. All I needed to do was set up this hash table, have an if else statement here. Instead of returning, I assign into my hash table. And the only other thing I needed to change was make sure the recursive call is this my new memoized version. Change every return to assigning into answers, and change every recursive call into a recursive call for my new memoized version. I could write a function. Memoizing a function is totally rote. You don't even need to know what the function does or understand it in any way. In fact, I could write a program that takes a function and memoizes it. Okay, I could write a Java program that looks at a Java source file and prints out a Java code for a memoized function of the same original function. Memoizing is rote. Okay, so let's make a note of that. Converting a function to a memoized version is rote, mechanical. We can even write a function which converts other code. Okay. In fact, depending on how your language is and how its model is, I could even write this as a function in the language. So sometimes go and actually show racket code, which takes in, there's a function, I wrote a function called memoize, and it takes in a function and returns a new function, which is a memoized version of it. So at runtime, it goes and does this, not even looking at the source code. Yeah, so this is good to note, okay? Because we're going to contrast that in a second, okay? Bottom up is pretty much the same thing. Bottom up works only because the other instances we wanted to look at were all smaller. And so I knew that if I have all the smaller ones already done, I don't need to make a recursive call. I know I can look it up. If somehow I had like negative value coins, if you have a negative 1 cent coin, I don't know why anybody would have a negative 3 cent coin or something like that. Yeah, you hope you don't have too many of those coins. If you do, throw them away. But If we had negative coins, I wouldn't be able to do this. If some of the values of C were negative, I can't fill up. I'm going to say, hey, what is coins memo bottom up of 17? If that depends on coins memo of 20, which then that 20 might recur and get smaller, that might be code that works in the full-fledged search, but doesn't work memoized bottom up. Okay, so bottom up doesn't always work. It usually works if you look on smaller cases. Okay, but that's the thing here. Let's go ahead and make a note of that. By the way, I can go ahead and run this bottom up code here. It's going to pass all my tests, and the running time looks just like the other memoized version. It just goes all the way through. Okay, so I'll leave us with that thought, and I'll tell you where we're going to start next time. Note that bottom up memoization lets us remove even the appearance of a recursive call. A little caveat depends on the recursive, what had been the recursive call better be on a smaller input. Be sure we recur on smaller inputs, which most of the time we do, so. Okay. Here's maybe the one drawback of bottom up versus top down. So here's the advantage. It doesn't even look like a recursive code. We don't have extra stack frames whatsoever going on. We just have this table, and we fill up this table. Okay. One potential drawback of bottom up, it computes values even if not needed. So suppose our top down, like say we started at 42, and we only needed we didn't need, maybe the answer of coins of 42 never needs to know coins of 33. I mean, it does, but imagine where the input of size 44 needed to know some of the things smaller than it, but not all of them. Well, bottom up, we compute coins of 1, coins of 2, coins of 3, coins of 33, coins of 34, coins of 35, all the way up, whether we need to or not, okay? So if it turns out not needed. Okay, but we will next time look at dynamic programming, which is just bottom up, except we don't need to keep a big table of previously computed answers. Okay, so I give the bottom up version as a segue into the next topic. If I were just doing memoization, I'd stop at top down, but bottom up is going to now sort of give us another idea for being clever that will work not all the time, but in some cases, the problems. Okay, I will see you on Thursday. And gosh, we finished this homework. Do I need to start thinking about an exam? I probably do, but my plate is really super full right now. So.
Hey, Professor, I have a question about the project that's on there for.
Oh yeah, the project. Yeah. Sure. We'll take an office hour on that, or an office hour question. Sure.
I was just wondering what was because it said it's due in 3 different parts. I was just wondering what was part 1 considered, because it doesn't really say on the webpage.
Really? I thought I put that on there. I'll definitely do that.
Unless I missed it. I didn't see anything.
Ooh, and that formatting is goofed up. It doesn't say part 1 of the, ooh, that's okay. Yeah, so, yeah, so I will go ahead and put exactly what it is. I started this myself over the weekend, and it wasn't actually like getting the first, I got half of parts 1 and 2 after a few hours. So it wasn't too bad. Yeah, so it's not in there. I try to get fancy and abstract over it and goofed up a little bit, as is shown in these parts here. Okay, but yeah, there are 3 parts. Part 1 is just getting the brute force algorithm working. Part 2 is getting divide and conquer working without sorting, or sorry, with sorting. And part 3 is getting the divide and conquer to work without sorting more than twice. Okay. So somewhere in there, I'll make that clear. I'll go ahead and get that fixed up right away.
Okay.
So I'm sorry about that. And that's a great thing to ask on the discussion board as well. But yeah, part 1, get the brute force working. So, which basically is figuring out the reading and the input, setting up your array, and just it's a very simple. The brute force is very simple. It's just look at all possible pairs, so it comes out easy. Oh, hey, good thing I talked about the. Well, I talked about the Python format strings, and they're actually used in the project here. So that's actually where I learned about the. That's where I learned about the Python format strings having this formatting, being able to say colon, and then some spec. I learned that just this weekend. The format strings themselves with just the curly brackets are awesome. Throwing in the formatting units is nice too, but unimportant. Okay. Take care. I'll see people on Thursday.
All right. Thank you.
Okay. See you, Con.